Last video we saw what happens when we have resistors in series. Now let's see what happens when we have resistors in parallel. Alright, let me pick a new color. New color will be magenta. There's my battery, positive, negative. There's my ideal conducting wire. Here's my ideal conducting wire. But then, and this is new, it branches off. And I have two resistances. I have one here. That was my printer making a random noise, if you heard that. I call them printer burps. And that's another resistance. And let's say that this has a resistance R1, this has a resistance R2. And of course, the non-intuitive convention is that the current flows from the positive to the negative terminal, but we know that the electrons are actually flowing in the other direction. And I want to keep saying that because I don't know. I think it's so important to just understand what's actually happening as opposed to the convention. Well, anyway, in the previous video we said, well, when we have devices or components in series, that the current through the entire circuit is constant. But let's think about what happens here. Let's think about what happens here. So we have these electrons. Actually, let's think about it from the electron flow. The electrons are flowing at a given rate, right? And then here they have a choice, right? Some of them can take this top path. Some of them can take this bottom path, right? So if you think about it, the flow of electrons in this branch plus the flow of electrons in that branch have to add up to the flow of the electrons in this branch, right? And then they're going to meet back up, and then the flow of electrons here. So if we think of it this way, and now I'm going to go back to the convention, that this is I1. So you have these electrons flowing at a given rate, right? This is the current right here. They're going to branch off, and maybe half of them go. If the resistances, we'll see if the resistances are equal. If these are kind of very, both of these branches have a equal amount of capacity in terms of how fast the electrons can flow through. If they're equal, or since we're going to current in this direction, let's talk about positrons, or I don't know, positive charges. If the positive charges, although as I just want to keep saying that it is not the positive charges that are moving, it's the electrons. But if we say that the lack of electrons can flow equally easily between both paths, that's if the resistances were the same. We could imagine that the current, the flow would split itself up, and then over here would meet back up, and then we would say that the current here would also be I1. But let's figure out what the currents going, let's call this current I2, and let's call this current I3. So I think it is reasonable, and you could imagine with water pipes or anything, that the current going into the branch is equal to the current exiting the branch. Or you could even think of it that the current entering, when the currents I2 and I1 merge, that they combine and they become current 1, right? I mean, think about it. In a given second, if this is 5 coulombs per second, I'm just making up numbers, and this is 6 coulombs per second, 6 I can't write properly, 6 coulombs per second, right? In a given second, right here, you're going to have 5 coulombs 5 coulombs coming from this branch, and 6 coulombs coming from this branch. So you're going to have 11 coulombs per second coming out once they've merged. So this would be 11 coulombs per second. So I think hopefully that makes sense to you that this current is equal to the combination of this current and that current. Now, what do we also know? We also know that the voltage along this entire ideal across this entire ideal wire is constant. So the voltage, let me draw that. Let me do it in another color, in blue. So for example, the voltage anywhere along this blue that I'm filling in is going to be the same because this wire is an ideal conductor, and you can almost view this blue part as an extension of the positive terminal of the battery. And very similarly, let me see, do it in yellow. We could draw this wire as an extension of the negative terminal of the battery. This is an extension of the negative terminal of the battery. Right? So the voltage difference between here and here, so let's call that the total voltage, or let's just say that, let's just call that the voltage, right? The voltage difference between that point and that point is the exact same thing as the voltage difference between this point and this point, which is the exact same thing as a voltage difference between this point and this point, right? So what we can say? So what is the total current in the system? If we just view this as a black box, that this is some type of total resistance, right? Well, it would be the total current in the system would be the total voltage, the voltage divided by, let's call this our total resistance, right? Let's say we couldn't see this and we just said, oh, that's just some total resistance, right? And that is equal to the current going through R1. This is that? Yeah, this is I1. This is 1 right here. This is current I1. Well, what's current I1? Well, it's going to be the voltage across this resistor divided by the resistance, right? That's what Ohm's law tells us. V is equal to IR, or another way we could say it is V over R is equal to I, right? So I1 is equal to the voltage across this resistor. Well, we just said that voltage is the same thing as this voltage, right? The voltage here is the same thing as the voltage here. The voltage here is the same thing as the voltage here. So the voltage across that resistor is still V. And so the current flowing across that resistor is V over R1. And the same logic. What is I2? I2 is this current. What is the voltage across this device? Well, that's just V again, right? It's the same thing as the voltage across this device. So it's V over R2 by Ohm's law. Well, all these V's are the same, so we can divide both sides of that equation by V. And we get 1 over the total resistance is equal to 1 over R1 plus 1 over R2. And you could make that argument if there was, if we had an R3 here, let's say that, we had another device and then it was there and there's R3, we would just, you could use the exact same argument and you would have a plus 1 over R3. And if you had Rn or, 10 of them, you would just keep at 1 over R4, R5, etc. So let's see if we can use this information we've learned to actually solve a problem. And I actually find that it's always easier to solve a problem than to explain the theory behind a problem. You'll see that most of these circuit problems, it's actually very basic mathematics. So let's say I have a 16-volt battery, plus minus, it's 16 volts. And let's say, and just to hit the point home that you always don't have to draw circuits the same, although it is nice if you're actually drawing complicated circuits, I could draw it like this. I could draw the circuit like this. And let's say that there's a resistor here. And then let's say there's a wire, and then there's another resistor here. And then this decides to do some random loopy thing here, and that they connect here, and that they come back here. This strange thing that I have drawn, which you will never see in any textbook, because most people are more reasonable than me, is the exact same, you can almost view it topologically, it's the exact same circuit as what I drew in the previous diagram, although now I will assign numbers to it. Let's say that this resistance is 20 ohms. 20 ohms. And let's say that this resistance is 5 ohms. What I want to know is, what is the current through the system? So, first we'll have to figure out what the equivalent resistance is, and then we could just use Ohm's law to figure out the current in the system. So we want to know what the current is. And we know that the convention is that current flows from the positive terminal to the negative terminal. So how do we figure out the equivalent resistance? Well, we know that we just hopefully proved to you that the total resistance is equal to 1 over this resistor plus 1 over this resistor. So 1 over, I won't keep right, is equal, what's 1 over 20? Well, actually, let's just make a fraction. So it's 1 over 20 plus 1 over 5 is what over 20? That's 4 over 20, right? So 1 over our total resistance is equal to 5 over 20, which is equal to what? 1 over 4. Right, 5 over 20. So if 1 over R is equal to 1 over 4, R must be equal to 4. So R is equal to 4 ohms. So we could redraw this crazy circuit as this. I'll try to draw it small down here. We could redraw this where this resistance is 4 ohms and that this is 16 volts. Right? We could say that this whole thing combined is really just a resistor that is 4 ohms. Well, if we have a 16 volt potential difference. Current is flowing that way, even though that's not what the electrons are doing. And that's what our resistance is, 4 ohms. What is the current? V equals IR, Ohm's law. The voltage is 16 volts. It equals the current times 4 ohms. That's current. So current is equal to 16 divided by 4 is equal to 4 amps. So let's do something interesting. Let's figure out what the current is flowing through. What's this? What's the current? I1. And what's this current? I2. Well, we know that the potential difference from here to here is also 16 volts, right? Because this whole thing is essentially at the same potential, and this whole thing is essentially at the same potential. So you have 16 volts across there. 16 volts divided by 20 ohms. So let's call this I1. So I1 is equal to 16 volts divided by 20 ohms, which is equal to what? 4/5. So it equals 4/5 of an ampere, or 0.8 amperes, right? And similarly, what is the amount of current flowing through here? I2. Let me do this in a different color. It's getting confusing. I'll do it in the vibrant yellow. So the current flowing through here, once again, the potential difference from here, that's not different enough. The potential difference from here to here is also 16 volts, right? So the current is going to be I2 is going to be equal to 16 over 5, which is equal to 3 and 1/5 amps. So most of the current is actually flowing through this, and that makes sense because the resistance is less, right? So that should hopefully give you a little bit of intuition of what's going on. And less current is flowing through here. So I1 through the 20 ohm resistor is, we could say, 0.8 amps. That's I1. And I2 through the 5 ohm resistor is equal to 3.2 amps. And it makes sense that when you add these two currents together, the 3.2 amperes flowing through here and the 0.8 amperes flowing through here, that when they merge, and then you have 4 amperes flowing through there. Anyway, hopefully I have given you some intuition on what happens when we put resistors in parallel. I will see you in the next video.